So in this lecture, we will study the analysis of single phase AC circuits. This lecture will cover the analysis of AC through a pure resistor, analysis of AC through a pure inductor, and analysis of AC through a pure capacitor. So let us start with the analysis of AC through a pure resistive circuit, or you can say through a pure resistor. The purpose of this lecture is to understand the behavior of an alternating voltage in a pure resistor, in a pure inductor, and in a pure capacitor. What is the relationship between voltage and current through these components as far as the phasor diagram is concerned, as far as the waveforms are concerned. Now, in this particular diagram, as you can see, you have a voltage source, which is alternating voltage source, which is V is equal to Vm sine omega t. Now, this voltage source is connected across a pure resistor R, which has certain voltage drop across it, which is VR. Now, the current through this resistor is, let us say, I. Now, the voltage V is Vm sine omega t. However, we also know that the instantaneous value of current I is given by I is equal to V by R. So this is the instantaneous value of current in this particular circuit. That means this current I will flow for one half cycle, it will flow in this direction. Let us say, let us assume, and for the another half cycle, it will flow in this particular direction. So it is given by I is equal to V by R. So if we substitute this V from here in this particular equation, so we get, let us put this here. So I is equal to Vm sine omega t by R, or I is equal to Vm by R sine omega t. Now this sine omega t is maximum at or when sorry so when omega t is equal to 90 degrees. So at omega t is equal to sine omega t is 1. So when sine omega t is equal to 1, I is equal to Vm by R into 1, that is Vm by R, is the maximum value of the current. That means when omega t is equal to 90 degrees, sine omega t is equal to 1, at that point of time, this current is the maximum in the circuit. So that means Im is equal to Vm by R. So if we assume that this is your equation number 1 and this is the equation number 2, so we can substitute this value in this equation. So we will get, if we substitute, we get I is equal to Im sine omega t. This is, for example, your some equation. Now, if we compare, let us compare V is equal to Vm sine omega t and I is equal to Im sine omega t. Now, if you compare these two equations, on comparing these two equations, you will observe that these two equations do not have any phase lag. have any phase difference. They do not have any phase difference. That means if you have to draw the waveform of these two equations uh, like this, so let us draw the voltage first of all. So voltage will be something like this. It is a sine wave. So 0 to pi and then 2 pi. One complete cycle is 2 pi radians. Now let us draw the current waveform. So the current waveform will be like this. This is the peak value. This is the peak value of voltage and this is the peak value of current. Similarly, here also you have negative peaks, minus Im and minus Vm. So in this waveform, this is the wave diagram of these two equations. Now in this wave diagram, you can see that both the signals are starting from zero. They're starting from zero. They're crossing the zero at pi radians and their one complete cycle is at 2 pi radians. Means they're completing their one cycle at 2 pi radians. So this shows that they do not have any phase difference. Phase difference is basically either any of the signal, voltage or current, is leading the another one or lagging the another one. So if leading and lagging is there between the signals, then we can say that they have certain phase difference. Difference in their phase, difference in their angles. So if we have to represent these two equations with the help of phasor diagrams, so how will you represent? The phasor diagrams of these two equations would be with something like this. The voltage phasor V and the current phasor I. As you can see here, V and I are the RMS values of the alternating voltage and current. That is V and I. Okay. So now if you see these two phasors, you must have noticed two things here. One is that there is no phase difference, and the second is that the current, this one is the current and this one is the voltage. So the current waveform is having low magnitude as compared to the voltage because the peak value of current is Vm by R. That is why its magnitude, or you can say its amplitude, is quite slow as compared to the voltage. So in this, so this is how you can represent. So from here in this analysis, we have understood that the voltage and current, as far as a resistance is concerned, if you see a resistance here, so as far as a resistance is concerned, so in a resistance, the voltage, because here if you apply KVL here in this particular, loop, the KVL gives you V is equal to VR, where this V is the RMS value of V and this VR is the RMS value of voltage drop across R. So you can also write it as or VR, means this phasor could be associated with the applied voltage or it could be associated with the voltage across the resistance. So you can say that in a resistor, the voltage and current do not have any phase difference. Or you can also say they are in same phase. They are in same phase. This is also we can say. Now, if you see here, we have got one equation this one, Im is equal to Vm by R, this equation number 2. Now if you take this equation 2, you have Vm is equal to Im into R. Now we know that Vm means the peak value is equal to, uh, sorry, basically if you divide this with under root 2 here, if you divide here under root 2 and here also if with under root 2, we know that the peak value divided by under root 2 is the RMS value. So we can write it like this: V is equal to I R, where V and I are the RMS values. So this is also one way of representing the equation in terms of RMS values. Now let us come to the next slide, in which we will discuss about the AC or the behavior of AC as far as a pure inductor is concerned. So in this diagram, if you can see, there is an inductor with inductance L connected across an alternating voltage source, which is V is equal to Vm sin omega t, and some current I is flowing in this particular circuit. Now, as far as your Faraday's law of electromagnetic induction is concerned, this inductor will have certain EMF. That EMF is E here. This EMF is known as back EMF. This EMF is induced to oppose its cause. Means this EMF will oppose the applied voltage, the alternating voltage which is applied here. So this E is given by E is equal to minus L di by dt. This is the equation for this L, this back EMF, because it opposes its cause, and you can also say that E opposes the change in current. From this equation, you can relate this. Inductor opposes the change in current. It does not allow the instantaneous change in the current through it. This is the characteristic of an inductor. Now, if you apply KVL in this particular equation, you will get V is equal to minus E. Or you can write V plus E is equal to 0. This is the KVL equation of the given circuit. So if you substitute it here, so you will have V is equal to L di by dt. So that means, this is for example equation number 1. That means alternating voltage is equal to back EMF, or you can say it is the induced EMF. Okay, so this is the induced EMF, right? Now let us solve this equation. So we can rearrange this equation. So let us rearrange this one. So we have di is equal to V by L dt. So we can write it like this, and we know that if this is equation number 2, so we know that V is equal to Vm sin omega t. This is given here. So let us simplify this further. We have di is equal to Vm by L sin omega t dt. This is your equation number 3, for example. Now, if you integrate this equation, equation 3 on both sides, so we have this one is equal to Vm by L, because these two are constant quantities. So we will integrate the sin omega t with dt. So we'll get this I here and then Vm by L. So this will give me minus cos omega t by omega. Okay, so we can simplify this one. It is Vm by omega L, and this is your minus cos omega t. So this minus cos omega t is also equal to sin omega t minus 90 degree. So because minus cos omega t is equal to sine omega t minus 90 degrees. So in this equation, this is the equation given to you, and this is some equation. Uh, Let us mark this as equation number 4, for example, and this is the given equation of voltage. Now, if we compare the given voltage equation with the current equation number 4, for example, so we will observe something. V is equal to Vm sine omega t. I is equal to Im sine omega t minus 90 degree. Now, if you compare these two equations, so you will see that there is certain phase difference between these two. The first thing you will see that there is a phase difference between V and I. Okay, and that is equal to 90 degrees. The phase difference is equal to 90 degree here. Second, you can say this means if they have a phase difference of 90 degree, and we can clearly see that the current is having minus 90 phase, right? So uh, the current I is lagging the voltage V by 90 degrees. So if you have to draw the wave diagram of this one, so the wave diagram will look like this. You have the omega t axis. The voltage will start from 0 because it is the reference. So it is like this: 0, pi, and 2 pi. So this is the peak value of voltage. This is your V is equal to Vm sine omega t. Now, what about the current waveform? The current will start 90 degree after the voltage. It will start 90 degrees after the voltage. So let us see where the 90 degree exists. 90 degree exists here, pi by 2, and this is your 3 pi by 2. So it will start from here, and it will cross the next 0 90 degrees after the voltage, and it will complete its one cycle 90 degrees after the voltage completes its cycle. So this is what we call as the lagging concept. So if you extend it here, so it will be, maximum, negative maximum at this particular point. This is the peak value here of the current, this one. So you can see, if you know the one half cycle of this is current. So in these two waveforms, if you see, there is a phase difference of 90 degrees, and that phase difference will remain constant throughout the function. Everywhere, if you see, this phase difference is 90 degrees, and it is maintained, right? So that means the current has started 90 degrees after the voltage has started. It has completed its half cycle 90 degrees after the voltage has completed. It has completed its one cycle, complete cycle, 90 degrees after the voltage has completed. So we can say that the current I is lagging the voltage by 90 degrees. As far as the phasor representation is concerned, or phasor diagrams are concerned, so because your voltage is the reference phasor, so we will take voltage along the x-axis. This is V, and the current, because it is lagging, so current will be here. So either we can say that the current I is lagging the voltage V by 90 degree, or we can say the voltage V is leading I by 90 degrees. So both the statements are True. So the phasor diagram can be this one or it can be this one. So this V and I, these are the RMS values of RMS values of V and I respectively. Now, if we have to represent this in terms of the RMS equation, that also can be done. However, if you come to this particular equation number 2, and if you see this equation here, so comparing these equations, we have got that this particular is equal to Im, because when this part is equal to 1, if it is equal to 1, this is maximum. So Im is equal to Vm by omega L. Now what is this omega L? That is the question now. What is this? Now if you compare, as far as your Ohm's law is concerned, if you compare, let us take this here, that equation. Let us erase all these ink from this one. Uh, no. So you have this. So as it is mentioned, Im is equal to Vm by omega L. Now what is this omega L? Now if you see, this can be written as Vm is equal to Im omega L. So this is somewhere what is resembling the Ohm's law equation, like V is equal to IR. So that means this particular factor is also something which is opposing the current. So this we call as inductive reactance. We cannot call it a resistance because resistance is the real parameter. Okay, this is something imaginary. It is imaginary quantity. Okay, not real. It is not real. It is imaginary. Now this is inductive reactance, and we represent inductive reactance with XL. So XL is equal to omega L. Hence, your Im is equal to Vm by XL. And the unit of XL is ohms. It has the same unit as the resistance has because the fundamental concept is same. This is something which is opposing the current, but virtually. It is not real component of the AC circuit. It is something which is virtual, which is imaginary, which is by virtue of the inductor. It is because of the inductor. So it is the inductive reactance, and it is given by this one. Now Vm is equal to Imxl, and if we divide it with root 2 here and root 2 here, so Vm by root 2 is the RMS value of voltage, and Im by root 2 is the RMS value of current. So this is the RMS value of voltage and current for a inductor. So this is how you can understand the behavior of an alternating current and voltage across a pure inductor. So in a pure inductor, you have the voltage leading the current by 90 degrees, right? There is one more component we have observed, which we call as inductive reactance, which is similar to that of a resistance, but not resistance because it is imaginary and resistance is real, right? So write it here, resistance is real, right? So it is measured in ohms, and this is about the inductor. Now let us come to the next topic, which is the analysis of pure capacitive AC circuits, or you can say analysis of AC through a pure capacitor. As you can see in this diagram here, you have an alternating source connected to a capacitor C. C is the capacitance of the the capacitor. So we are given V is equal to Vm sine omega t, and this is, let us say, our equation number 1. Now, if we have to understand the nature of the voltage and current here, we will see it through a different perspective. Okay, so this I is the current which is given by. As far as this capacitor is concerned, the current in this capacitor is basically the rate of change of charge, dq by dt, and q we know it is equal to cv. So here v is the voltage applied. The same voltage will be appearing across this capacitor. So q is equal to cv. So we will put it here. So I is equal to dq, not q, sorry. Um, it is dcv by dt. Now capacitance is a constant parameter, so it is c dv by dt. So I is equal to, now we will put this v in this particular equation. So I is equal to c d vm sine omega t by dt. Now, so vm is also a constant. So c vm d sine omega t by dt. Now the derivative of sine with respect to t is cos omega t. It is now cvm omega cos omega t. Now cos omega t, as per the trigonometric rule, cos omega t can also be written as sine omega t plus 90 degree, or I is equal to Im sine omega t plus 90 degree. So this is, let us, equation number 2. Now here Im is omega cvm, because this particular equation will be maximum when sine is equal to this component is equal to 1. So we have this one here. Now if we compare equation 1 and 2, so the observation is that now v is equal to vm sine omega t and I is equal to Im sine omega t plus 90 degrees. So the observation is that, the first observation is that v and I has the phase difference which is equal to 90 degrees. And the second observation we can see is that current is leading the voltage by 90 degrees. So if we have to draw its waveform, so let us draw the waveform here. Mark this as equation number 3 first. So let us draw the waveform omega t, because your voltage is the reference here. This is v is equal to vm sine omega t. So it would be like this. So this is 0, this is your pi, this is your 2 pi. And this is the voltage v is equal to vm sine omega t. Now let us draw the current waveform. Now the current waveform will start 90 degrees before the voltage waveform has started. From this, that means your I will follow the cosine wave, right? So it will start from here, 90 degrees prior. So this is your current, which is I is equal to Im sine omega t plus 90 degrees. So you can see here the phase difference will be 90 degrees. This is your 90 degrees everywhere. So that means it has completed the one cycle 90 degrees prior to the voltage everywhere here. So if you extend it, it will go like this. So that means your current has started, you can see here, it has started 90 degrees before the voltage. So it means that the capacitor will acquire the voltage across it 90 degrees after the current has passed. So this is what it indicates basically. Now if the phasor diagram is concerned, let us draw the phasor diagrams also. Now let us represent the voltage phasor, which is a reference here V, and the current is leading the voltage by 90 degrees. So either you can say that I leads V by 90 degrees, or you can say that the voltage or V lags I by 90 degrees. Both statements are true. Either you can say that current is leading, or you can say that voltage is lagging. So now let us take this equation number 3. From equation 3, we have Im is equal to omega c Vm. So we can also write it like this: Im is equal to Vm by 1 upon omega c. Now what is this omega c? Okay, so again you can compare this with I is equal to V by R. So or let us say Z basically, if we write more specifically Z, which is impedance. So this is something which is having the similar nature as that of resistance. It is again opposing the current. It is because of the capacitor, but it is not real, it is imaginary. So this omega C is we call as capacitive reactance. It is capacitive reactance, and it is given by omega C is equal to Xc, or not Xc basically. It is uh, your Xc is equal to 1 upon omega C. It is 1 upon omega C. Now this is also measured in ohms. Right? So we can write this equation as Im is equal to Vm by Xc, or Vm is equal to Im Xc. Now if you divide it with root 2 and here also with root 2, so this is the RMS value. V is equal to I Xc. So in this we have understood, the first thing that we have understood is that as far as your capacitor is concerned, the current leads the voltage, or the voltage lags the current by 90 degrees. The second thing is that there is one more component associated with the capacitive circuit, and that is capacitive reactance. Capacitive reactance is something which has the similar nature as that of resistance, but it is not real as resistance, it is imaginary. We will write it here also. Xc is imaginary, and it is measured in ohms. So, so this is summarized here. The whole concept has been summarized here. Uh, we have the resistor, inductor, and capacitor, and their phasor diagrams have been shown. Phase angles are given here, and the remarks are also given. Whatever we have studied in this lecture have been summarized in this particular slide. So this is about today's lecture. Thank you so much.